Hi, in this video, we want to take a look at partial credit models and their generalizations. Okay, so the situation is that we have some questions that have some like integer values or could be proportional to integer values. Let's say we could have 0 to 5, 0 to 10, 0 to 7. Now, in a rating scale model, all the questions had the same possible scoring values. Here, questions can have different values, but they need to be distinct. So there's going to be and they're going to be ordinal also. So both rating scale model and partial credit models require that we have ordinal data or integer data, and but rating scale models, all questions have the same number of possible levels, like 0 through 5 for all questions, 0 through 7 for all questions. Partial credit, we have different numbers. Now, both of them require that it's always integer values, at least in the representation. All right, so we can't have a situation where a student gets 0, 1, 2, 2.5, or 3. That won't work out. It needs to be 0, 1, 2, 3, something like that. Now, in the rating scales model, we have to have constant space between the thresholds for each of the levels. Now, we don't have that here. Rating scale models, it's a question of how much shifting over left and right we have on the distributions. In partial credit models, we have a lot more flexibility. Now, but it comes with a catch. It's possible that a certain value, a certain level is not the most likely for any ability level. And so that's something that we may want to consider when we fit our model and start checking out individual items. Now, this example is modified from the Modern Psychometrics with R by Mayer. Here's the GitHub website for the code. See, there we go, just zooming in a little bit. All right, so let's go ahead and get the adult self-transcendence inventory. All right, so this is a self-reported measuring of complex target constructs of wisdom. How about that? And so there are 5 dimensions. There's self-knowledge and integration, peace of mind, non-attachment, self-transcendence, and presence in the here and now, and growth. Okay, so the data frame has a little bit over 1,200 observations, and there's 25 individual questions. Now, here, it has 3 or 4 categories per item. So if I want to use a rating scale model, I can't use the whole data set. I would have to limit it to the ones that either have 3 or 4. In addition, we have 2 covariates. So, rating scale model would not be the best fit right off the bat. So I want to use a partial credit model. And here are the individual items. All right, so now I'm going to go through and I'm going to set it up so that I'm only printing 2 digits, significant digits when I print things. That way I'm not getting blasted in the face by numbers. I'm loading the data. Now, some of the items are reversed from each other. So there's different scalings depending on the type of one. So let's look at 1 and 2. They're different. I often engage in quiet contemplation. I feel that my individual life is part of a greater whole. I don't worry about other people's opinions of me. I feel a sense of belonging. My peace of mind is not easily upset. My sense of well-being does not depend on my social life, and so on. So there are, questions that has like a reverse scaling to them, and those reverse scalings are included in this vector here. These are the reversed ones. Now, these are the vectors that indicate which columns correspond to each of the individual dimensions. So let's look at the personal growth one for this example, because this is what the author of the textbook did. All right, so we're going to use the ERM package to fit a partial credit model. Now, there are other packages that will do this, but this is a very nice way. This connects very well with the other videos that we have. So partial credit model is a generalization of rating scale model. Each item has estimated item category parameters. Now there are more parameters on this one because there's more flexibility. So if I have fewer observations, this may not be a good choice. Remember, the more parameters I want to have in the model, the more data I need to have to really make that coherent, to be able to fit well. Otherwise, I'm prone to overfitting. Items do not need to have the same number of categories. That's a big difference from rating scale models. And responses are ordinal and coded as integers starting at 0. Now, in rating scale models, the distances between category thresholds is constant, but in partial credit models, this is not the case. This is a huge jump up in flexibility. So rating scale models, we're reducing the number of parameters, and this will actually give us the ability to work with less data, but I'm also, imposing more model structure. So a good rule of thumb when I'm doing my model building, the more model structure I impose, the less flexibility, the more I impose on my model, then really I need less data. The more flexibility I'm letting the algorithm, fit to the data, the more flexibility you have, the more data I have. So for a partial credit model, I really need to have a lot more data than I do for rating scales because of the additional parameters. So all categories have an endowment probability greater than the other categories. In partial credit model, it's possible for categories to never have a greatest endorsement probability. All right, so what this is saying is that for what we'll see in a moment, we're going to take the latent variable for the data set that we fit from factor analysis, kind of pseudo factor analysis. And so we're going to find that latent variable. And then there's like a scale on the x-axis, and then each level of the response for the item has a likelihood distribution in relation to the latent variable. All right, so whichever response is the most likely for that particular value of the latent variable of that person is the one that we see is most likely. Okay, well, it's possible that, let's say if I have 0 through 5, it's possible that level 2 is never the most likely level to occur for that question. It's either going to be 0, 1, 3, 4, or 5. And so something about this, the more levels I have, the more likely I am to encounter this. If skipping over levels in likelihood is a problem, does not work for your situation, this is not a good model for you. Now, partial credit models are in the Raish family. And so remember that they have a unidimensionality assumption of the latent variable. They have parallel item characteristic curves, so parallel curves, and local independence. Okay, so if these three things do not fit our situation, this is not the model to use. Okay, so now let's go ahead and fit our partial credit model and take a look at our thresholds. Okay, so here, remember, we reduced it down just to the personal growth items, and we've got 11, 15, 23, 17, 14, and 18. Now, you'll notice that I sorted these guys by their location. I chose this order of the numbers just so that as we work through this, it'll be easier for us to interpret what's going on. But we can see that the location is shifted over. And then by the spread of the distribution, that will tell us how, where these actual threshold cutoffs are. All right, so here we can see that these questions have 0, 1, or 2 as possible responses. These have 0, 1, 2, or 3. Okay. All right, so now let's go ahead and plot it to kind of get a feel of what's going on. So here are the questions. So on item 11, if they score, let's say, I'm just going to approximate this. If their latent variable is less than -1, then we expect them to get a 0 on item 11. If it's between, let's say, -1 and 0.5, we anticipate it's most likely, in terms of modeling, most likely to have a level 1 for item 11. And if their latent variable is greater than 0.5, then they are most likely to have a 2 for item 11. And that's how we read this. And we can see like a histogram here of the distribution of the latent variable. So this gives us a nice representation of what's going on. Now, I sorted the items so that you can see that the centers go from left to right, and I put the ones with just 0, 1, or 2 levels in a group, and then 0, 1, 2, or 3 in a group also. So we can, interpret what's going on with these. Now, a generalized partial credit model, this adds a discrimination parameter to the model. So this is similar to slope in logistic regression. So generalized partial credit models do not require parallel item characteristic curves. Okay, so in fact, expect it to not be parallel. All right, so if, there's some aspects of this that we can get some things that don't really make a whole lot of sense. But usually if I have a lot of data, it won't be an issue. So remember, when I start adding more parameters, I need more data for this to be a coherent model to not overfit. So if I don't have sufficient data, I want a simpler model structure for sure, because the having a complex model for very little data is not coherent. Okay, so here, let's go ahead and we're going to use the LTM package, latent trait modeling. We're going to use RACE model with generalized partial credit, and then we're going to do a generalized partial credit model. Also, we're using the same function, but by constraining to RACE, I'm imposing the RACE model structure. So here we're imposing parallel curves. And now let's take a look at the two. All right, so when I run this on the ST data set, we can see that we have a the statistical difference between the two. Now we know the RACE model is a simpler model structure, and there's a statistically significant difference between the two. So we come to the conclusion that the generalized partial credit model is better than the RACE model. It's worth the added complexity to have a discrimination parameter, that is slope, in terms of logistic regression. All right, so now let's go ahead and plot these together so we can get a feel for what's the difference. Okay, so here is item 1 for the RACE model. We're just going to look at item 1, item 2. And we can see that these are very similar, curves over here. But there's a lot more flexibility down here. And here's how I'm getting the code to make the plots. All right, so very similar, not much of a difference between these on the RACE model, but now the generalized partial credit, because of the ability to have more flexibility in what's going on, we can see that these are very different distributions down here. These are very similar because they have parallel slopes. Now, there is a difference in the horizontal shift, but the slopes are parallel if I look at the cumulative or the CDFs. Now, another version I can approach this is with graded response models. So graded response models, they're very similar to partial credit models. The difference is in how they're fitted. So operationally, on what I'm trying to pull out of the information is very, very similar. These are very similar models from a utility point of view. The difference is the mathematics and how they're fitted. Partial credit models are fitted with mean adjacent logistic logits, while graded response models are fitted with cumulative logits. All right, so You'll grade. So there's just a mathematical difference. To truly understand it, we need to understand the differences. We need to write down the formulas. I don't want to get real deep into it. It's in modern psychometrics with R if you want to take a look. And so graded response models estimate probability of being a category or higher. All right, so that's because it's a cumulative log. So a category or higher because of CDF, and graded response models can handle questions with differing numbers of categories, once again, like partial credit models. Now here, each item in a graded response model has a parallel curve. The difference between the curves is a location parameter called the category boundary location. All right, so that's how much it's shifted over left and right. So let's go ahead and take a look. So I'm going to do a graded response model with the ST data set. And let's go ahead and look at our factor scores. And let's go ahead and do some plotting. All right, I want to scroll down to the plot. So here we can see that we have cumulative logits. These look a lot like logistic regression, right? And so category 1, 2, or 3. Remember, it's modeling the probability of 1 or greater, probability of 2 or greater, probability of 3 or greater. So if I want the probability of 3, I just get it here. If I want the probability of 2, I have to take the probability of 2 or greater minus the probability of 3. If I want the probability of 1, I take the probability of 1 or greater minus the probability of 2 or greater. And then over here, 1 minus the probability of 1 or greater gives me the probability of 0. Now, these parts of the code just extract aspects so we can see what's going on in the plot. And here we can look at the actual curves. Now, you'll notice that previously it was 1 or greater, 2 or greater, 3 or greater, and I had 3 curves. Well, you'll be like, hey, what about 0? All right, well, here is the 0 and the 2, the 3, and the 4. Okay, so this curve is 1 minus the modeled likelihood of 1 or greater. All right, well, that's all I've got for you. Take care and goodbye.